All right, so let's move out of here. Let's call this just the sourcing basics, just so we have it in the example file. Let's maybe copy and paste this thing and call this Vellum splitting. And let's actually do our actual work in here. So we don't really need these source points anymore, because we're just going to be starting with just one sphere. We're going to delete the ground plane. We don't really need the gravity in here either. We just want to source just a single piece of geometry. We don't even need the Vellum source, to be honest. We could just source this sphere in here. So we could do op input path like that, and with the constraints like that. And let's disconnect the subsolver for now. And now we're back to a sort of a basic thing where we just have this sphere. Let's put this to one substep. Yeah, so that's pretty much it. So from here we want to start splitting this thing up. So I actually build this setup first outside of this main network. Let me go like this. Because we need to start splitting this thing. We can actually just do this here in SOPs first, just to build our little split. And then after that, we can implement it in our solver. Right now, we don't really need to care about any of the time stepping stuff. So there's multiple ways, of course, to sort of split a piece of geometry in half. I'm just gonna use a Voronoi fracture to do it. So I'm gonna scatter some points, scatter 2 points on this thing, 2 points. I'm gonna do a Voronoi fracture. So Voronoi fracture will fracture this thing in 2, effectively. You can see if I put a exploded view, you can see it splits it in 2. And if I change the seed, see, it's pretty much splits it just straight down the half all of the time. We could change the seed. We could put $F here, so it changes every frame. So if we would do this, and it would effectively just change the way that it sort of fractures every frame. So we have something fractured now. But if we have a look at this thing, so like we cannot really start inflating this because there's no really geometry here on the inside, right? If we want to inflate this as a bubble, we could just try this as we could just copy our constraints here, just test this out, throw this in here, and let's put a Vellum solver. Let's just have a look at what this looks like. All right, like that. So if let's remove the gravity. Let's increase the rest length so it just inflates. So you can see this is not going to work because we have this little piece in the center. So we need to remesh this. We put let's put a remesh in between it. So we put a remesh. This will effectively just remesh the entire thing, add some more geometry. We can change the target size to be a little bit smaller so we get a little bit more geometry. And if we now, let's play, you see it does work, but it sort of sticks into each other because some things here are sort of interpenetrating, which we probably don't want. Pretty easy fixes to do that. So what we could do is we could do something like a peak. And peak will allow us to sort of push this thing in or outside. So you can see you can sort of inflate it or outflate it or deflate it. Effectively, all it's doing is just sort of adding or subtracting the normal to the position. You can make a peak like this yourself really easily. Oh, it's hard coded, but you could just do this in a VOP, and you can just add a normal to it, and then you get the same thing. So let's do it very slightly. I think this should probably already be enough. Right, you can see now, if we play, you can see them sort of inflating outwards. So that already works pretty well. And we could, for good measure, maybe add a little bit of a smooth. to slightly smooth out maybe these edges here. And this actually seems to break it, so maybe we don't want to do that too much. I think I might just get rid of the, because we could either do like this, or we could just get rid of the smooth. I think the smooth does make it look a little bit nicer. So let's do the smooth. A little bit like that. Let's do the peak a little bit more like that. Let's have a look if this holds up. Seems to hold up pretty well. So we have this sort of coming apart. If we're going to do this in a solver, actually what we want to do is we want to do this multiple times, right? So in like once we're inside a solver, we actually want to start doing a for each loop, for each connected primitive, we want to sort of do this again. So we'd be in the for each loop, where we would do it by connectivity. So we would do connectivity, creates a connectivity called class attribute, which checks for connected geometry and it gives a class. You can see two classes. You would put it to class, and then we would get sort of two passes of this, and then we would effectively just do this again. Again, in the solver, this is not gonna be multiple for each loops, but now to just demonstrate here in SOPs and turn off single pass, and yeah, now you can sort of see it's sort of being split again. Of course, here like it's not like it looked a little bit weird because they're not inflated yet, but you can see if you were to do this multiple times, you can sort of individually keep splitting these things. So let's implement this in our solver. All right, so let's grab our little for each loop thing, and let's go in here. And just remember, by the way, we're not going to go in there. We're going to go in here. Remember, we cannot really start playing this before we also implement all of the other stuff. So from now on, we're sort of just going to work on the static setup for a little bit, because once we start splitting this, it will immediately break if we play, because we haven't dealt with the constraints yet. So we're just gonna go in here and we're gonna just be dealing with some stuff in our SOP solver. Let's just make a new SOP solver, just for good measure. Let's make a SOP solver. And let's call this run on Geo. Let's do another one, a regular SOP solver, and call this run on constraints, and plug this in. And for this one, we're gonna say that it should run over the data name constraint geometry. And if you're confused about like how you can find these names or what these things are called, if you ever forget, you can just, if you look in here in your geometry spreadsheet, which I always have open here, I like to have my geometry spreadsheet always open in the back. If you don't know that, you can split views top, bottom, left, right, like this, or like top, bottom, and you can make then something a geometry spreadsheet. So I like to keep that open. Anyway, so if you do that in a dot network, like in here, you can actually see sort of the context here change to a dot network contact, and you can see here Vellum object. If you go in here, you see all of the things sort of contained in our Vellum object. You can see there's collision geometry, constraint geometry, and patch geometry. So we're gonna be focusing on this geometry and constraint geometry. There's also this, if you have collision geometry, that's of course, if you put any colliders in here, it's gonna be in here. Patch geometry, if you make a Vellum source, it has patch name. Effectively, this is just kind of like the group name. So it will, like if you source this, it would be pulled in here and would be called Vellum source 1. If you'd have another one, it would be Vellum source 2. It's kind of like just the group that it's sort of in, and it's going to behave like. Yeah, so we can have a look in here at sort of these things. So we're going to run over these geometry and constraint geometry. So if we play through this, and we can have a look here. So here we can just see the geometry, and if we go in here, we will see the constraints. Right. So we will first need to start working in here. And again, this is all plugged into a multi-solver. And the way this is going to work is this multi-solver is going to iterate on this Vellum object. And then it's going to do these things from left to right. So it's going to solve Vellum, then it's going to solve geometry, then it's going to solve constraints. Yeah, it allows you to say the primary solver, which is set to 0, which is the first one. I guess if you'd want another one to be the primary solver, yeah, you could change that. You can make them mutual factors, or you can turn it off. For our sake, this doesn't really matter. You can see something here changes about sort of if they're sort of related to each other. This effectively says that if something happens in here, that it should also affect whatever is in here and in there. If you turn it off, these things are only going to influence sort of the main thing that you're sort of iterating on. For our sake, it will work regardless. Yeah, so just like this. So yeah, let's start actually working in our geometry. Let's copy this thing. Not sure if I still have it copied, but let's copy it. And let's go in there. Going to geometry. And I want to sort of move this down, and I want to sort of branch in here. So I want to let's play a couple frames, and let's have a look. All right, yeah. So I need a connectivity before it. Oh, keep accidentally sometimes pressing just my caps lock. So I need a connectivity before it, else it's not going to work. I want to put it to primitive, and now this should work. So you can see I can actually now play this, and nothing will break. So because here is a this is the output. This is connected to the dop geometry. It's outputting this thing here on the left. This thing on the right here, we can, like, it doesn't matter if we have it highlighted. It's going to sort of output whatever is here, and here we can just work on this little part. So it's going to output this side, this part we're going to work. So kind of like what we're going to be doing is we're going to split our geometry here, and then here we're going to set up these h attributes, and then once this h sort of reaches a specific value, we're going to replace the thing that's going in here. We're going to sort of swap it out with the thing on the right. So before we can even start doing that, of course, it's not enough to just do this thing, because here we're splitting it. We also need to create these new constraints and everything. So we actually need to do another for each loop, for each connected piece. So we need to do another one because kind of like we don't want to just run over what is created here. So here we are creating the sphere, and then in here we have these two parts. But we want to run over these two parts individually. So we could either make this for each loop inside of this existing for each loop, or we can just do it after the fact. Doesn't necessarily really matter. But you can see now here we get these other two parts. So this is going to run over this, and then in that thing we can start creating these constraints. So we would need to do we could do another Vellum balloon. Configure balloon. Could plug this in. Then we would get our thing like this, and then we could do a Vellum pack. So we can sort of pack up these constraints so they only get one output. So we can do like this, like that, and like that. Then we can put them here in the output. So we get one output over here. And then over here we could do another Vellum unpack. And then we would have our geometry here on the left. Let's call this, I guess, split geo. And on the other side, split con. And let's go. All right. So you can see here we have geometry and we have constraints. And here we, of course, still have our main thing. So the idea would be to sort of, in the same time step, sort of switch to this geometry. And then in our constraints, move to this constraint. So in the same time step, and then it should sort of replace it all, and it should theoretically work. So we can just try this really simply by just, before we set up any of the age attributes, let's just manually try this. Let's put a switch here. Let's put a switch. So this switch is going to switch from this to this. Let's say we want to do this $F above frame 30. So it's going to, after frame 30, it's going to switch from this input to this other input. Now, we will need to do this again. We want to do this in our constraint geometry as well. Let me open my thing over here on the side again. So we have can have a look at our splitting setup. Let's go in here. Let's go into constraint. So here on the right, we're gonna have a look at the constraints. So we want to actually object merge something in here. We want to object merge our constraints from this other solver in there. Then we want to do another switch. And we want to switch on the same time, so we can just copy and paste this input, copy and paste relative references. So this is gonna do the same. So if this goes to 1, the other thing also goes to 1. So effectively, after frame 30, this will switch to the fractured geo and then the constraints as well. And technically, this should now work. Let's have a look. Right, so it keeps, okay, it keeps doing it now. You can see it does work. So it keeps splitting it up. Score is not what we want, but you can see it does work. Like the Vellum doesn't break. It just keeps splitting it up every frame because it's effectively just stays at the second input. If we just want to check it be just at the other input, what we could do instead is maybe $F percentage means modulo 30 equals 1. What this will do effectively, right? So percentage modulo 30 will effectively just keep counting from like 0 to 30. Maybe I can turn off the simulation. I can show you the output. Yeah, so if I do this, it will effectively just keep counting until it gets to 30 and then it repeats. That's what modulo does. So if I then put equals 1, it will evaluate to 1. I should put this between brackets, by the way. Equals. Right, there we go. So now it will evaluate to 1 every 30 frames. So you can see now it's going to do this every 30 frames. And I probably want, because you see it also does it on the first frame. So what I could do if I don't want it to immediately split, I could do a second switch maybe. Let's put a null here. Let's do a second switch. And let's say this one, $F above frame, I don't know, 20. So let's do 20 frames of not doing it. And then after that, it will sort of switch to this other input. And then it will keep doing it. So let's do the same over here. Oop. All right, here we go. All right, so let's have a look at what this will do. Auto update. All right, there we go. Play. All right. All right, you can see we have a splitting Vellum sim. So of course this is not really like it's not inflating yet, but I mean you can see like we do have something that works. Quite cool. So in order to inflate, we need to actually override these constraints in here. And what we kind of want to do for that is we actually want to go level up, and we want to actually grab our pressure constraint here. So if you remember, these constraints will have different names, different groups. We've already used this a while before. We want to rename our constraint here for our pressure. We want to output a group and want to output it to pressure, the pressure group. And we want to do the same in the one over here, where we also have a group and we want to call it pressure. And then we want to do a Vellum constraints. or I want to do Vellum constraint properties, sorry. Like that. And we want to put it in particle forces. We want to run it over pressure. And we want to say rest length scale equals 1. So this will just inflate it to a value of 1. So let's have a look what this will do. And, oh, not rest length scale. So this is a multiplier of the existing scale. We actually want to override the existing rest length. So it's always 1. So let's have a look what this will do. Right, there you go. Now you can see. So this will sort of override any existing existing rest length. So if we go in here, if we just have a look in the, in solver, let's have a look at the constraints that we have here. Let's blast out our pressure constraint. Right, so you can see there's a rest length. It's not 1. If we put that thing on, it will override it. If we use this other thing, rest length scale, it will sort of work as a multiplier on the existing rest length. So I guess if we put this to 3, it will also sort of work. So I guess it depends on kind of what you want to do. You can put it to 4 if you wanted to inflate it more. So I guess either is fine. Either set a static rest length or use it as a multiplier. This will always produce sort of exactly the same sort of size inflation because it's just going to override it. This is going to depend on the size of things that are created. So if one is created smaller and the other one's created bigger, this will work as a multiplier. So it will create the smaller one 4 times as big, the bigger one 4 times as big. Yeah, it kind of depends on kind of what you want to do. So you do see they are sort of being pushed away quite far. So this is because of the forces at work in the Vellum solver. If you want to reduce that, you can go to Vellum solver. You can go to velocity dampening, and we can increase the velocity dampening. So this will dampen the velocity, so they sort of stay together a little bit more, like this. And you do see this weird thing happening here. It's because this thing is being fractured and remeshed. It's not recomputing the normals, so that's why it looks weird. So we just need to recompute the normals. We can either do that after the sim or in the sim, but if we want to look at it in the sim, just see what it looks like, we probably want to just do this inside of the simulation. So we could just put a normal here, just recompute it there, and then okay, I guess I don't do it there. Guess maybe I should do it there. Okay, for some reason visualization seems to still be a little bit off. This is weird. Doesn't necessarily really matter, to be honest. You can just do it if we do it after the fact here, then it does work. Okay, then I have no idea why it's acting weird, because I'm doing exactly the same thing here. I could I don't know, if I put it here, then it should also work, because then it's just constantly doing it every frame. Right. And that does work. I guess it was, yeah, the reason why it was not working is because it's recalculating the normal on the not inflated yet geometry. So that's why it was looking weird. So, but now we have, we have a splitting Vellum sim. Pretty cool, right? And again, we can either do it like this, or we can put it like that. You can see if we do the other one, they get progressively a little bit bigger. So I guess it depends on the type of effect that you wanna achieve. For cells, it wouldn't really necessarily make sense if they get progressively bigger. So something like this probably makes more sense. All right, so we have our basic thing going. Now we can work on getting this a little bit randomized. So now they're sort of all splitting at the same time. which may be what you want, maybe not what you want. But I mean, we have a working setup now, so we can make it a little bit more interesting. So you can start working on this, doing it by age and then randomizing when it switches, etc., etc. So let's try that. So let's make a wrangle. Let's do attribute wrangle. Call it create age. Put the primitives. We actually want to do all of these other things after this. We want to first create our age. Right. Let's say f at age plus equals at time inc. And we probably, let's make this work for the substeps as well. So we gonna go in here. Let's make a integer substeps equals channel I substeps. Let's link that up. And then we're gonna do divided by substeps. All right, there we go. So it works. So now we should have a we have a primitive age, sort of increasing. Now we can use that age to start sort of splitting some things up. So let's do that in a second wrangle. Let's do wrangle. Actually, we want to move this connectivity. We want to move it over here so we can use it in our wrangle as well. That's primitives. Let's create a random based on our class. Rand equals rand at class. So we're going to create a random value based on the class. So if we have a look at this, you can see we have a class going from 0 to 3. If we were to write this out, you can see we get a random value for every class. Right, now we can fit this value. Could say rand equals fit 0, 1, because we want to fit something that is between 0 and 1 to something else. So we could say, right, r, and then let's say 0.3 to 1. I'm going to fit a machine like between, why is it a ring? Between 0 and 1. Oh, not r, rand. Yeah, I often use r as a placeholder variable for my random stuff. All right, and then we can say that maybe that if at age is greater or equal than rand, and also rand maybe is greater than 0.3, because we don't want to do it every time, else it's going to split a lot. I can show you the difference in a little bit. Let's first have it set up like this. And we're going to say, right, let's set an attribute, maybe I add my split equals 1. So this is going to create an attribute called my split, which is sometimes going to be 0 and sometimes going to be 1. I guess in this case it's always going to be 1 for some reason. Oh yeah, because of course our age is above, because we haven't sort of reset our age, which we also need to do. Because of course after they're split, their age needs to be reset. So we should do a primitive wrangle sort of after this whole thing. We should do that on, let's do it here. I'm gonna do primitive. We're gonna say, right, f at age equals 0, and we also want to say I at my split equals 0 as well, because we want to sort of, once they split, they should restart counting again from 0, else they will just keep incrementing this age. So for now, if we're going to be pressing play, should be able to go in here. And you can see they will sort of, once they split, boom, they will sort of go back to 0, start counting again. And my split will be 1 here. And then after that, it will sort of go back to 0. Now we have this my split attribute. We can actually start sort of removing this stuff that we have here. We could do it with a switch if. And this is the reason why I don't want to use the this one, subsolver constraint geometry, because we also need to do it on constraints later, and we cannot use switch if in a compile block. We're going to use switch if. I'm going to say attribute value, and I'm gonna say, all right, we're gonna say that or what was it called again? It was called mySplit, and it's going to be a primitive attribute. It's going to be greater than or equal to, let's say 1. So if it's 1, oh no, it's always, because it's 1. It's not. It's always going to be 1 because it's a thing. So it can just be equal to. You don't need to be greater or equal to. Just if it's 1, it's going to switch. And then we need to do the same in our constraint geometry. We need to make sure that this also happens on our constraint geometry. So maybe instead of doing it like this, let's actually put this wrangle maybe on 2 sides. Let's put it on both our constraints and our geometry. Right, now I want to go into this thing on constraints, and I want to load in our geometry here. So I want to do another object merge. I want to load this geometry you have here. I want to transfer something to our constraints from our geometry. I want to transfer H and mySplit. And then we can do the same with this switch if. I can just get rid of this. You can say, right, if switch if is equal to 1, it's going to switch. And again, so it's grabbing now on the constraints. It's gonna grab from my regular geometry. It's going to grab the geometry. It's going to transfer H and mySplit to the constraints as well. And then if it's going to be 1, then it's going to switch over. Let's have a look what this does. Let's actually have a look here. All right, let's see. Right, so this is switching, and this is merging in the geometry. On the same frame, we should have our geometry here. We should have, I think actually if we were to load this, then it might actually work. Because this happens, so now it's going to grab the thing before it switches. Let's have a look if this actually does anything. All right, there you go. So the reason this works now is because this was switching, and then it would grab the reset value here, and it wouldn't have the mySplit, and so then it would break. So let's call this null out prefracture. And now it's going to transfer these over perfectly fine. And now let's have a look at what this is going to do. And it does seem to always split them now for some reason. We need to tweak our little wrangle a little bit, I think, because I don't want them to always split. Let's have a look at the randomization here. Let's say only if rand is above 0.9. So let's see if then what will happen. It's going to wait a long time because it's going to wait for rand to be above 0.9. Which only happens 10% of the time, which I guess is not going to be a lot. All right, let's tweak it a little bit. Let's make it 0.7. Let's maybe, oh, I know what's going on. Let's put it to 3. So of course, like it's going to do the random on the class, but it's always going to be the same random because, so like nothing is ever going to change. We probably want to do at class plus at frame. So it's going to change the random that's being called every frame. So now we should get something more interesting. It's still splitting them all at the same time. Now let's have a look if we make this threshold a little bit bigger. What's going to happen? Still happening. Oh, wait, I forgot a step. Yeah, so what's happening here is that if mySplit is equal to 1, it will switch this, so it will replace the entire input, but there's no check here to see which one it should fracture. So this is stupid, but again, like I like to leave some mistakes in so you know what's going on. So we should actually also do a switch if here, if it should even fracture them, else it of course is not going to change anything. So we're going to do attribute value switch. So what do I call them again? My split primitive equal to 1. All right, let's have a look if this now works. Still seems to be splitting it. Oh no, okay. Like you can see, some will stay. This one is not splitting. You can see. So some are splitting, some are not splitting. Right, so we have it working. Beautiful. Yeah, so you can see some will split, some will not split. And you can change these values on the threshold over here. Right, so with that out of the way, let's cache this out actually. Let's do a .io. And let's load this in. So let's go and let's load DOP network. And let's say that we want to load our Vellum object. And we should get rid of this part over here. We want to do, if you chose particles, it will grab the geometry, as you can see here. And we want to do another one. And we want to also load the constraint geometry. Get the constraint geometry. Now we can do a Vellum IO. So we can cache it out. So some additional thing that you actually might want to do before you cache this out is if you want to texture these, you would want maybe some rest geometry on this. So you would want to put a rest here. And you want to put a rest, if you go in here, you would want to create a new rest, probably here. So if you don't know what rest geometry is, so this effectively stores the position of this geometry. So you can use it to sort of map a texture on it, kind of like a UV, but you can use it for triplanar mapping. So you can sort of project it sort of during render time. So if let me show you what I can do, for example, with this. If I do an attribute noise, noise vector. So if I were to put some color on here, CD, right? If I do some color on here by default, you can see it's going to float through, like the noise is going to float through this thing. So if it goes to, so you can see it's not really sticking on it, right? But if I do this on my rest that I generate, these rest positions that will be sort of set the moment it fractures. See now, I get a static noise on these things, and you can use this in your triplanar mapping when you render this. Yeah, you can use this to. Let me show you how you would do that. I'm actually not using any textures in my cells, but if you were to do it, you can see I did experiment with it a little bit before it. There's a triplanar mapping which you could put some textures in here. You see, like I was experimenting with it. I didn't really use it, but you can use a primvar reader. You could use a float tree, and you could type rest. And you can use this position in the position. And now this will sort of map this texture based on this reference position. So you can texture these. So even though they're splitting, you can still get some nice textures on it. You don't need to. So that's how you solve sort of the UV problem. Anyway, let's cache this out. I'm going to say cells, and let's do 300. Let's maybe stop this thing after a certain amount of frames. let's maybe, if we want them to stick together a little bit more, because you see now they're sort of floating apart, we could actually increase this velocity dampening so they actually stick together a little bit more. And if you want them to sort of bulge up in something like a sort of a shape, specific shape patch, then you could, what I did in my sim, put a collision geometry in there, so they will just sort of just fit into that shape eventually. Doesn't really matter for what we're doing here. Let's just cache this out. Cells. Let's change one more thing. I don't want them to do this anymore after a certain frame. So let's say that do enable solver, and we're going to do $f below frame 250. So it's going to be 1 until we get to frame 250, and it's going to disable it. I'm going to do that on there as well. So it's only going to do this splitting until frame 250, and after that it's just going to run. And now let's save this out. Right, so the patch that's being created here is not too big, so it's cached pretty quickly actually. So looks pretty cool. Yeah, now finally, if we want to sort of maybe instance this on a text like I did in my example, what I first want to do is I want to create a proxy for this because instancing a lot of these might get really slow. So maybe I want to do a sphere, give it some something like this, make it a little bit bigger. Let's array this to our original geometry. So we get like a little proxy for our actual shape. So we could do geometry. We could say geo proxy for.bgo.sc. Save it out. 300 frames. Something like this. And then maybe for our render stuff, we actually maybe just want to, we don't care for this entire cache. We don't care for the constraints. We might want to do a Vellum post process after this. Maybe you might want to maybe peak them a little bit to sort of do something like this. And then let's do, like you'd want to maybe attribute delete some stuff. Let's see if there's actually stuff that we don't need. We don't need class, we don't need age, don't need mySplit, don't need name, don't need any of these. We only want to keep only want to keep velocity and rest. And then we can call this render geo. So I'm going to save this out again, but now for the actual geometry. Right, and now I could start instancing this. So maybe do could do anything pretty much. We could also do this inside of a pig. Let's do a pig for now. We can do whatever you want on it. Let's do points from volume. Something like this. Let's maybe jitter them a little bit. Now let's do, so we want to now use my path sequencer. Again, this is not by default in your Houdini. This is it's a AZA toolset that I made. It's paid. You can get it with a discount if you buy the source files to this tutorial, or you can just buy it directly. There will be a link to these things in the description. So if you're interested, you can do it. There will be a link to the example of what it does as well. Effectively, it's an AZA toolset that allows you to sort of grab geometry caches or geometry from disk and sort of instance animated geometry on points and then time offset it, and it's quite neat. So if you type dvh initialize attributes, I want to start initializing attributes on this. So this will initialize an age attribute, as you can see here, and I can say the like the start attribute that I'd want to them to start on. In this case, it's fine from the first frame. Then I'm going to do tvh geosequence. Geosequence allows me to set up a geometry, so instance a geometry sequence. I don't want to do it from scene, I want to do it from disk. So I'm going to add a plus icon, and I'm going to go in here, and I'm going to go to hip. I'm going to go to geo, render geo 1. I'm going to plug it in there. You can see they're quite big, so I'm going to do tvh scale instances. I'm going to plug it in there. I'm going to change the global scale, and I'm going to maybe also do maybe a little bit of a random scale. Maybe I want a little bit more points. Let's make it a little bit smaller, and let's do orient instances as well. We get a little bit more of a random rotation, which might be a little bit nicer. Or let's actually just do a randomized orient. Might actually look better in this case. Right. So you can see, we can see our splitting happening on our sphere. Maybe what we actually want to do, by the way, before we do this, because now they're sort of coming, it's sort of already existing. Maybe we want, in the first couple of frames, we want to actually scale in the sphere. So let's do a transform this down, save this out. And we want to do this on the proxy as well. So, all right, now we can see them sort of appear. Okay, this we probably need to reinitialize this, else it's going to look a little bit weird. Let's have a look. Why is this looking weird? Oh, yeah, we need to... okay, go to open my scene again. Instancing sometimes can keep stuff in memory, so you get some weird issues. Right, so there was a weird viewboard thing. Now it's working, so you can see it's all sort of splitting now. It's happening all at once now, which probably doesn't look that nice. So we want to do a tvh retime instances. Want to randomly offset maybe some of this. So some will start a little bit sooner, some will start a little bit later. Right, now we actually get a nice, and we don't think we even need the proxy that I made for this. So what the proxy, effectively why I made this for, if you have a ton of points, it might get, of course, slow to instance this, and you could put the proxy in. So you could have something that's sort of fast to work with if you look in your viewport, but it's not too bad if we just look at it like this. So we have a whole pig growing like this. And now we could, if we want to render this in Karma, for example, we could grab a out here. We could do a lob network. Put a stop import. And now if we want to import this, it's important that we preserve these instances that we created with this thing. The way you do that is you're going to primitive definition, packed primitives, point instancer. So that's going to create a point instancer from it. And then we can load the, let's actually load this thing, the out. So we're going to load it in here. So this is actually going to create a point instancer with all of the prototypes that we have here. So all of the different frames that it's loading. So you can see it's just grabbing these things from disk. Now you could just do a environment lights, do like HDRI. Make a camera. Okay. All right, there we go. Make a camera. There we go. Maybe we want to do a little bit closer, something like this. Maybe you want to do like a quick material, quick surface material. Put it in here. And let's call it cells assign material. Oh. Want to maybe, by the way, call this cells as well. So import path, so it's actually named cells. We want to assign a material to cells, and we want to assign our cells material. And then we could, I don't know. Kind of depends what you want to do with the look. I don't want to spend too much time here on creating a look for this, but like you could do something, maybe even add some transmission. It's going to be slow. Let's just do it like this. Yeah, so you can see we have now a big sort of shaped from cells. Again, if you want to use these rest attributes in these materials instead of doing this quick surface material, how you would do it is instead of doing the quick surface material, what I would actually start doing is I would go material library, turn off Karma XPU. You would do material library. You would make a Karma material, cells. We'll do a triplanar projection. Put it in, for example, base color. Then I could point this to a texture. So I have a UV texture here. Oh. Could just grab this. So effectively what a triplanar is going to be doing. Oh, no, I don't want, I'm really messing this up. Right, there we go, like that, and file Z. Triplanar is effectively going to create sort of 3 cameras, top, side, side, project a texture, and sort of have a blend between it. And it's going to do that based on these rest positions. So if we do a primvar reader, float 3 rest, we're going to load in these rest positions, going to put it in position. If we want to do tiling on this, we could do a multiply here to sort of set up some tiling. And let's assign this material actually. And let's have a look. See, it's just a, I've just assigned this thing, just a UV, just to sort of show you that it works. So if we sort of scrub through this, you can actually see it's actually sticking. So you can actually texture this to your heart's content. Then we have, yeah, we have a cool Vellum splitting simulation. Of course, like you can make this a lot crazier. You can run a lot longer simulation than we have here. This one is quite short. There's not that many splits happening. Yeah, but of course you could have them split a lot more. If that's what you want, you could like you can have sub steps on this as well. We could slow down the time scale. If you don't want them to be that explosive, you could do something like this. You can, if you reduce the velocity dampening, you could have them go like that. Yeah, just have at it, make something cool. But yeah, this is how you split Vellum simulations. And again, it doesn't have to be cells. You can cut off geometry, like cut off limbs, do anything crazy that you want. I might do future tutorials as well where I make some more examples of this. For example, if you'd have a soft body, you could cut off a limb. You could do it dynamically instead of prefactoring it. You could actually sort of tear it off, like depending on like where sort of a thing hits. You could sort of cut it in a solver, stuff like that. Yeah, this is effectively how we do it. So I hope you enjoy. I don't think there's really that many tutorials explaining how to do this. I haven't really seen any online. So yeah, this is how you split Vellum simulations. Yeah, so if you want to download the source files, there will be a link in the description. So you can get them on Gumroad, Patreon, or other places as well, depending on when you watch this. If you want path sequencer as well to sort of do this whole instancing setup, if you buy the source files to this video, you get a discount code to get path sequencer 50% off, which should be the same cost if you buy path sequencer directly, but now you also have these files. So then you have both, which is nice. If you support on Patreon, you'll be able to download both in the same tier as well. So you get path sequencer plus the source files to this thing. So, and it helps support the channel so I can continue making these videos. Well, hopefully you like this, and see you in the next one. Bye.